So we've worked out from the previous, when I mentioned it earlier on, that we want to have high pressure, low temperature, but we may have to compromise. So, so we might, yeah, okay. So stage, yeah, okay. So stage one in the Haber process, we get hydrogen and nitrogen gases are pumped into the compressor through pipes. The gases are compressed to about 200 atmospheres inside the compressor. So there's our high pressure. The pressurized gas are pumped into a tank containing layers of catalytic iron beads at a temperature of 450 degrees centigrade. So the question is now, why have we got it so hot? I'm not sure why it's so hot, to be honest, at the moment. Let's have another look at this, make sure that I've read this correctly. So we want the exothermic reaction, which means we want colder temperatures. Yes, we do. Okay. I'm not sure. Maybe for whatever reason we need to have it hot for maybe for the catalytic iron beads to work. I'm not sure. Anyway, and then we've got this unreacted hydrogen and nitrogen. So if you look over here, then we look at the actual diagram. Here's the gases. Now for your GCSE, they would like you to know that nitrogen. Where do you get the nitrogen from? Where do you get the hydrogen from? The nitrogen comes from the air. So we collect nitrogen from the air. Air is mostly nitrogen. If you didn't know that, it's about 70-80% air. Air is 70-80% hydrogen. Oh my God's sake, nitrogen. Air is 70 or 80% nitrogen. Is what I was trying to say. So that's where we get the nitrogen from the air. The hydrogen you get from natural gas, so as in the fossil fuel. So you put these two ingredients through these tubes. They come to the compressor where they get pressurized, and then there's a kind of like, I guess there's probably some sort of pump that forces it this way around. The hydrogen and nitrogen come down to here. We've got these iron catalyst beds. So in the previous reaction, I didn't talk about anything to do with the catalyst. So that might affect things, right? So the catalyst is going to speed up the reaction. Comes down here. We then have, because it's a reversible reaction, we're never going to get rid of the nitrogen and hydrogen completely. So we're going to have a mixture of some of the reactants, the nitrogen and hydrogen, plus the product, ammonia. Then this is the clever bit, or one of the clever bits. They cool the whole thing down, and ammonia becomes a liquid, whereas the nitrogen and hydrogen stay a gas. So because ammonia is a liquid at that temperature, it condenses at the bottom, and then we can just collect it with a tube or pipe. Now the gas, the nitrogen and hydrogen, gets pumped back up around and repeats the process. So this is the way that we've got a mixture of hydrogen, nitrogen, and ammonia, and we use something similar to fractional distillation. Well, it is fractional distillation, really. Here, so they condense it so as only the ammonia will condense, whereas the other two carry on traveling around. That's the cleverer bit. I sort of talked about this already, but I want to see if it clarifies anything that I didn't explain. The graph below illustrates the effects of changing temperature and pressure on the yield of ammonia obtained. So, yeah, okay, I was right. This is good news. So as you can see, a higher temperature would reduce the amount of ammonia, and we can also see as we increase the pressure, the amount of ammonia increases. So it's still not clear why they've chosen what seems to be a relatively high temperature. But let's see. Yeah, by following any of the curved lines on the graph, it can be seen as the pressure increases, so does the yield. By following the vertical line upwards from the x-axis, in other words, looking at the different colours, the temperature decreases the yield. increases. And now we know why, because we talked about how we can affect the equilibrium point. The actual conditions used must be chosen depending on a number of economical, chemical, and practical considerations. So it's been a bit vague there, but they're basically saying that clearly the best conditions would be the hotter the better. No, would be the cooler the better, and the higher pressure the better. However, you can't keep on increasing the pressure because it costs money to get things to be a certain pressure, and there might be some reason why we can't have a lower temperature, but I'm not sure. They looks like they're going to talk about here now. So the economic considerations. Like all industries, the companies that manufacture and sell chemical goods do so to make a profit. Part of the industrial process is the economic decision on how and where to design and implement the manufacturing site. Okay, blah, blah, blah. This is not that useful. This is the bit I was looking for. The higher temperature would favour the reverse reaction. Yeah, I said that. As it is endothermic. So a higher yield of reactions would be made. If a lower temperature is used, it favours the forward reaction. I said all this. Okay, so here's the explanation of the compromise. However, at a lower temperature, the rate of reaction is very slow. Okay, so we have to have it relatively high to get the rate of reaction high. However, not too high, otherwise the reverse reaction would be favoured. So 450 is a compromise. And let's have a look at the compromise for the pressure. Lower pressure would favour the reverse reaction. A higher pressure would favour the forward reaction. However, high pressures can be dangerous and very expensive equipment is needed. So for the higher marks and questions about this, you need to understand the compromise. So we know high pressure, lower temperature would be best for shifting the equilibrium point. However, there are constraints. So we have to have it fairly high temperature because otherwise the rate of reaction will be very, very slow and we'd be waiting forever for it to finish. And so there's the compromise there. And with the pressure, we can't have it too high because otherwise it's dangerous and expensive. Okay, there's more to learn about there, but we kind of went over that bit before, and we'll have to stop there anyway.